Hey everybody, and welcome to the worked questions video for lecture 10, which was the last video on the D block elements and actually the last proper video with questions for the inorganic chemistry part of the course. So this is the last worked questions video. First up, we're with question 10, which is looking at working out the crystal field splitting energy, or at least relative crystal field splitting energy, for pairs of complexes. And we have to identify which of them has the higher crystal field splitting. And in each case explain our answer. So we've got three pairs of complexes or complex ions, and what's quite nice is they all use a different effect for what splits causes the crystal field splitting to be bigger. So in the first case we're looking at two titanium chloride complexes. The first one hexachlorotitanate, and the second one is a tetrachlorotitanate complex. Now the difference here is that one of them has 4 chloroligands and one has 6, and that means that this one is going to be tetrahedral and this one is going to be an octahedral complex. Now this makes a big difference. If you remember, delta T is approximately 4/9 of the value of delta O. So the crystal field splitting energy of a tetrahedral complex is about 4/9 of that of an octahedral complex. This means that for this question, this pair, it's the hexachloro complex that has the large crystal field splitting energy. And this is, we'll have another question on crystal field splitting energies a bit later, and this will pop up again. But in general, octahedral, bigger than tetrahedral. The next one is two very similar nickel 2 plus complexes, so a tetrachloro and tetrabromo nickelate. The nickel's in the +2 oxidation state for both of them. Both of them have 4 ligands. They're both tetrahedral. So the only difference now is what is the ligand. And this is where the spectrochemical series comes into it. So I'll give you this in the exam, and if you want to look it up now, it's on page 1284, right at the bottom. And it's basically a long series of all the common ligands, and it shows in order which ligand gives a larger crystal field splitting energy. So at one end you've got weak field ligands, and weak field ligands don't split it that much, and at the other end you've got strong field ligands, and these split it a lot more. Now, if you look at the crystal field splitting energy, the spectrochemical series on page 1284 at the bottom, you'll notice that bromide and chloride ions are both weak field ligands, but the chloro ligand is slightly more stronger field than bromo. So in that case, it's the tetrachloro complex that has the large crystal field splitting energy. Finally, we're now looking at two hexaaqua ion complex ions that are essentially the same. They've both got 6 aqua ligands. It's both iron. The only difference now is the charge on the complex, and actually therefore the oxidation state of the ion. So water is a neutral ligand, which means the oxidation state of the metal is essentially the same as the charge on the complex ion. So in this case we've got iron in the +2 oxidation state, and in this case we've got iron in the +3 oxidation state. Now this one's quite easy to remember actually. If you've got metals in the same complex such as this but different oxidation state, is essentially the higher the oxidation state, the higher the crystal field splitting energy, or the higher the charge on the metal, because that's the same as well, the higher the crystal field splitting energy. So in this case it's the second option that has the higher value of delta, and that's because iron's in a higher oxidation state, it gives a higher crystal field splitting energy. Next up, question 11, we're looking at which of these complexes we'd expect to be tetragonally distorted and explain our reasoning. So when we hear the word tetragonal distortion or tetragonally distorted, what it means is when we have an octahedral complex, such as I'll draw here, with ligands at these 6 octahedral geometries, the bonds along the z-axis, so these, have been lengthened slightly, and that's a tetragonal distortion. It can also actually be a shortening of these bonds. It's essentially along the z-axis, which is this one, the bonds have been changed from the normal, lengthened or shortened. And if you remember, this is because of something we call the Jahn-Teller effect. So this is, tetragonally distorted. If you read that, Jahn-Teller is the thing that springs to mind. And this occurs when we have a doubly degenerate ground state. So the ones we're looking at here are D4 and D9 especially. It can happen with sort of a D1 and D2 because, the electrons can be in multiple configurations, but they're such low energy that we don't see anything happening. So it's just D4 and D9 that we care about for this tetragonal distortion. And the reason this is I'll explain it for D9, but you'll see it's exactly the same for D4, just with unpaired electrons. If we have our T2G and EG orbitals drawn out here, for D9 we've got them all paired down here, and we've got 2 here, so that we've got 1, 2, 3, 4, 5, 6, 7, 8 electrons at the moment. And the question is, where do we put the 9th electron? We could put it in this one or in this one. So that's what's meant by double degeneracy. If you think of D4, it's exactly the same except unpaired electrons. So we'd have 3 unpaired electrons down the bottom. And if we've got a high spin complex then for D4, good point. I'll write high spin there because it is only for the high spin ones. The 4th electron could go in either EG orbital. So that's what's meant by double degeneracy. But let's, for the sake of argument, put it here. By lengthening the bonds along the z-axis, there's less interaction of the ligand with the any orbitals with a z component, and therefore these are lowered in energy. So if we say that this is the dz squared and this is the dx squared minus y squared, and then down here we've got the dxy, dxz and dyz. So I've done 2 completely different types of z's there, but you get what I mean. So this will change the splitting pattern slightly to be anything with a z component lower. So let me get rid of these labels so I can draw it easier. From here, we'll end up getting 2 that are lower, the dxz and dyz orbitals. To compensate for this lowering of energy, the dxy will actually go slightly higher. And then we have the same thing here. This is not drawn to scale at all. The dz squared is again stabilized because it's got a z component, and these bonds along the z-axis have been lengthened to lower the interactions. And then the dxy minus x squared minus y squared is higher in energy again. So this is what the Jahn-Teller effect is briefly, why it occurs, and the electrons, why it occurs. Then we've ended up getting rid of this double degeneracy. We've stabilized one of the orbitals, so now there is a stable electron configuration. We got 1, 2, 3, 4, 5, 6, 7, 8, 9. There's no longer a question about where that 9th electron is going to go. Same with the 4th electron for a high spin D4. So we lengthen the bonds along the z-axis to stabilize what would be a doubly degenerate ground state. So then, for this question, that's a very long explanation to get to the actual question. Which of them would we expect to be tetragonally distorted? What we're looking for is a high spin D4 of a D9 complex. So all of these ligands that are shown, so water and ammonia, are all neutral ligands. Therefore, the charge on the complex is the same as the charge on the metal. That makes it easier to quickly go through this. So copper in its metallic state has copper 0 has an electron configuration of 3d10 4s1. And if you remember, this is an exception to the Aufbau principle. It fills the d orbitals before the s because it has that full d shell then. And then when we take 2 electrons away, because it's copper 2+, this ends up leaving us with a 3d9 complex. So turn to green. This one we can expect to be tetragonally distorted. It has that d9 configuration that we were talking about that lets the Untitled effect arise. Next up, we've got nickel, and nickel as a metal is 3d8 4s2. This is again same as the charge on the complex, so we're looking at nickel 2+. This one then has an electron configuration of 3d8, so let's put a big red cross through that one. No tetragonal distortion for a d8 complex. Manganese as a metal, 3d5 4s2. Again, it's 2+, so if we're looking at manganese 2+, we're looking at a 3d5 complex. Again, not a high spin d4 or a d9, so big fat cross through that one, no tetragonal distortion. Finally, chromium. Chromium, like copper, is the other one that has the exception to the Aufbau principle, 3d5 4s1. So instead of fully filling the 4s orbital first, it has 4s1 3d5 because this half-filled d orbital is much more stable. This time, the charge on the chromium is 3+, so we're looking at chromium 3+, and this is then 3d3. Again, not a high spin d4 or a d9, another big fat cross. So the only one of these that we'd expect to be tetragonally distorted is copper, and that is because it has a d9 electron configuration. Again, very long explanation for this, essentially going into the Untitled effect in a bit more detail than was necessary, but it does explain the reasoning very fully. But the quick thing to remember for looking for things that will have the Untitled effect be tetragonally distorted, high spin d4 and d9 is what gives you the answer, and then the Untitled effect and this stabilizing of any Z component orbitals is the explanation of your reasoning. Question 12 is all about working out whether complexes are going to be high spin or low spin. So we're going to start by working out the crystal field stabilization energy for both high spin and low spin D4 complexes, and then using some data that we've been given for the crystal field splitting energy and the pairing energy, whether two complexes are going to be high spin or low spin. So let's start off by working out these expressions for the crystal field splitting energy. So let's draw the electronic configurations for both. We'll start with high spin and then do low spin down here as well. So it's D4, so we put in the first 3 electrons, fine, and with high spin the fourth one goes into an EG orbital up top, and with the low spin the fourth electron pairs up in another T2G orbital. Now if you remember, each electron in a T2G orbital stabilizes the complex by minus 0.4, and each electron 0.4 delta O, sorry, and each electron in the EG orbitals destabilizes it by plus 0.6 delta O. So we can work out the expression for the high spin D4 quite easily. That is, we've got 3 in the T2G orbital, so we've got 3 times minus 0.4 delta O gives us minus 1.2 delta O. We've got 1 electron in the EG orbital, so it's plus 0.6 delta O, and this gives us a final expression of minus 0.6 delta O. So let's write that up here to keep track of it. High spin expression is minus delta 0.6 delta O. For the low spin, we have to take into account the pairing energy, because we've got 2 electrons paired up in one of the orbitals, and these electrons are going to repel each other. So this takes energy. So first let's look at the delta O term though. Again, down the bottom, each electron gives 0.4 minus, stabilizes it by minus 0.4 delta O. This time we've got 4 electrons down there, so it's 4 times minus 0.4 delta O. This equals minus 1.6 delta O. But as I said, we've got a paired up electron. This takes energy because those electron-electron repulsions. So we've got the plus P term. We'll write this up here for safekeeping as well. Minus 1.6 delta O plus P. Because now we finished with the first part of the question, I need some room to do the second part of the question. So with the second part of the question, we're going to take these expressions, and work out the crystal field stabilization energy for the hexaaqua manganese 3 complex and the hexaaqua rhenium 3 complex, and work out which of these will be high spin or low spin. Now, there is a quick cheating method we can use for this, just by looking at the relative values of delta O and P, and that is if it takes more energy to pair it up than to make the jump. So if the pairing energy is larger than delta O, it's going to be high spin. And that is, yeah, as I say, it takes more energy for it to pair the electron than to jump up across this split crystal field. And then the opposite gives us low spin. So if it takes less energy to pair up, then we get a low spin complex. So we can already predict that this will be low spin and this will be high spin. But that's kind of cheating. Let's prove this is actually the case and use these values and show how much more stable it will be to be high spin or low spin. So with the manganese complex, there are two options. We'll do the high spin and low spin. So manganese, for the high spin complex, we've got minus 0.6 times 250, and that will give us a crystal field stabilization energy. And if it was to be low spin, it would be minus 1.6 times 250, because remember we've got minus 1.6 of the delta O, and then we've got to plus the pairing energy because we're putting some electrons together. So minus 1.6 times 250 plus 300. And then we've got exactly the same expressions for rhenium, but with its own values of delta O and P. So minus 0.6 times 400 and minus 1.6 times 400 plus 180. Now, if you get out your calculator to do these, I already have them on a piece of paper next to me, so I don't spend ages doing it. You get values of 150 and so minus 150 and minus 100. Remember, these are all in kilojoules per mole. And for rhenium, minus 240 and minus 460 kilojoules per mole. So now, since it's a stabilization energy, we're just looking for the lowest energy. Like the lowest energy is the most stable configuration. So for manganese, we can see that minus 150 is lower than minus 100. So therefore, manganese does indeed favour the high spin complex. And the rhenium is minus 460 is much lower than minus 240. So for that case, for rhenium, the low spin complex is much more stable. It forms low spin. One little bonus bit, if you remember back to the last question on Jahn-Teller effects and tetragonal distortions, this complex, we could actually expect tetragonal distortions because it's a high spin D4 complex and it has that doubly degenerate ground state. Question 13 has us looking at various manganese complexes and ordering them either in increasing values of delta, so the crystal field splitting, or increasing intensity of colour. So we'll start with part A and looking at the increasing value of delta, so how much the splitting energy is between the T2G and the EG orbitals, or the E and the T2 orbitals if it's tetrahedral. And you'll remember this is quite similar to the first question in this video. They gave us pairs of complexes and was asking us which has the largest value of delta. And we saw there were 3 pairs and there were 3 reasons for why one was bigger than the other. And we're using all 3 of those reasons again this time, but to make a series rather than just identifying pairs. So the things to look out for, which we talked about last time, were whether something's tetrahedral versus octahedral, where the ligands are in the spectrochemical series, and then finally what the charge is on the metal cation. So first let's look for a tetrahedral complex. These generally have very small values of delta, and this is because if you remember, delta T is about 4/9 of the value of delta O. So if you can find something tetrahedral, we can imagine that's going to be the smallest one. Now all the ligands that we're looking at here are monodentate, so we can just look at how many ligands there are around it. That's going to be the same amount of donor atoms, and then we can work out whether it's octahedral or tetrahedral. So in this one we've got 6 ammonias, 6 cyanos and 6 cyanos, so all 3 of these are going to be octahedral. This one's just got 4 chloroligands, so this one's going to be tetrahedral. So we can imagine that that has the smallest value of delta. Next up, we're looking at the difference in ligands. So this one has an ammonia ligand, and these have 2 cyanoligands. Now, if we look at the spectrochemical series, which you'll remember shows us whether we've got weak field or strong field ligands, or how weak and strong the ligands are, and stronger field ligands give a larger splitting energy, so a larger value of delta. In the spectrochemical series, which you can find on page 1284, I'll put it up in the corner there, we can see that ammonia is a weaker field ligand than the cyanoligand. So that means that ammonia doesn't split it so much, therefore this is going to have the next largest value of delta. And then finally, we're looking at 2 very similar complexes. The only difference is the charge on the metal center. So the cyanoligands are minus. Each of them has one negative charge. So knowing that the charges on the ligands and the charge on the complex ion, we can work out that this manganese is in 2+ cation, and the other manganese is a 3+ cation. Now, with the charge with the metal, if you remember, it's the higher charge, so higher Z equals a larger value of delta. So then this one will be the next highest value of delta, and the manganese 3+ will have the highest splitting energy of all 4 of these. In part B, we've got 4 more manganese complex ions. These aren't all the same as last time, by the way. And this time we're ordering them in increasing intensity of colour. So with colour, we have 3 things to look out for again, and these are called selection rules. So the intensity of colour is based on how many of the selection rules are adhered to. And yeah, if you have a pale colour, it means fewer of these selection rules are adhered to. So they're what's called forbidden transitions. So the 3 selection rules we need to worry about are the Laporte selection rule, which says that there's got to be a change in orbital in this transition. So D to D transitions aren't actually allowed. The second one is the symmetry selection rule. So this is the transition can't occur from orbitals of similar symmetry to one of the same symmetry. So, for example, G to G transitions aren't allowed. And the final selection rule is the spin selection rule, in that spin shouldn't change. So the way I actually find this easiest to do it is in the opposite way. So we'll go from the one with increasing, from the most intense to the least intense. So instead of labeling them 4, 3, 2, 1, we'll label them 1, 2, 3, 4. So the most intense in this one is the first one. It's this manganese or the permanganate anion. Now this one is the most intense because it's a charge transfer complex and it adheres to all of the rules. So when I say charge transfer complex, what I mean is that most of the colour we see in transition metal complexes arises from a transition from the lower d orbitals to the higher d orbitals. So either T to G to EG in octahedral complexes or E to T2 in tetrahedral complexes. Now this is always forbidden because it's a D to D transition. In a charge transfer complex, such as this permanganate anion here, the transition is actually an electron from the p orbital of the ligand to an empty d orbital of the metal center. So that means that even this first rule, that there has to be a change in orbital, is satisfied. So this satisfies all the rules and it is our number one. It's the most intense. Just a note for your learning, and mainly the exam actually. This is the only charge transfer complex for this course you're going to need to know of. I'm not going to ask for intensity of colour in the exam and put in a completely different charge transfer complex. So just know that permanganate is the only charge transfer complex you have to know. But there are a lot of them in chemistry. So there are a lot of very intense colours, and ligand to metal charge transfer is a really big thing in general, but for our exam this is the only one you need to know. Now we're just left with 3 other complexes, and all of these are D to G transitions, as I was saying. So they either go from T2G orbital to the EG orbital in octahedral complex, or from the E to the T2 in a tetrahedral complex. Now the big thing here is that from an octahedral complex it's a T2G to an EG orbital, therefore this rule isn't satisfied. Whereas in tetrahedral complexes we're going from E orbital to a T2, there's none of these symmetry symbols such as G, therefore it's an allowed transition. So tetrahedral compounds are more intensely coloured than octahedral compounds because they satisfy this symmetry selection rule. So let's have a look. We've got this manganese with 6 ammonia ligands, therefore that's octahedral, and this manganese has 6 cyano ligands, so this is also tetrahedral. So it's just this one, the manganese with 4 chloroligands. This is a tetrahedral complex, therefore it doesn't satisfy the D to D rule, but it does satisfy this symmetry rule, and it also satisfies the spin selection rule. So this is going to be the next most intense, number 2. Now finally we've whittled it down to these last 2, the hexaamine manganese 2 and the hexacyano manganate 3. These are both octahedral. The transitions for both of them are D to D, and it's T2G to EG in both of them. So neither of these first 2 are satisfied. So it's just coming down to the third selection rule for these 2, that the spin shouldn't change. So let's have a look at the electronic configuration of the manganese and see in which of these the spin will change and which of them it won't. Because that's the only difference between one of these, the spin will be able to stay the same, and one of them it won't. And that will tell us which is more intense than the other. So in this first complex on the left, ammonia is a neutral ligand, so the charge on the metal is going to be the same as the charge on the complex as a whole. So this is manganese 2+. And in the other complex we're looking at, so the hexacyano manganate, each cyano ligand has 1 minus charge. It's an anion, so that's 6 in total. It's 3 minus 6, so this will be manganese in the +3 oxidation state, or a 3+ cation. This obviously changes the electronic configuration of the manganese. So manganese in its +2 oxidation state, or manganese 2+, is a D5 metal, and manganese 3+ is a D4. So the next thing we need to look at is how the electrons will be filled. So under here I'll draw this one, and here we'll have this one. So all hexacyano complexes are low spin, and this is because in the spectrochemical series the cyano or cyanide ligand is right at the top. It's the strongest field ligand, and there's a really big crystal field splitting which is larger than the pairing energy. So hexacyano complexes are always low spin. So let's put our 4 electrons in like this. Now this manganese with the ammonia ligands, that one's D5, and that one, this crystal field splitting isn't so large. Not only is it ammonia ligands rather than the cyano ones, which are a less strong field in the spectrochemical series, it's also only a 2+ metal cation rather than the 3+. If you remember from earlier on in this question, the first one, a higher charge means a larger crystal field splitting. So this complex is going to be high spin. So let's fill up the D5 there. Now I think, hopefully it becomes quite obvious which one is going to adhere to the spin selection rule and which one isn't. So if we look at this high spin D5 complex, wherever we take an electron and try and put an electron, it will always go from being an up arrow to a down arrow. Like the spin has to change. There's no way for it to stay the same. So then this one doesn't adhere to the spin selection rule. So then this one is the weakest, and this one does. This one we could have a one jumping up like that. The spin can stay the same. So then this is number 3. So there we have it. Increasing intensity of colour and also increasing crystal field splitting energy for quite a few manganese complexes. Final question for all of our worked questions is a nice, short, simple one, believe it or not. Copper 2 complexes are coloured, whereas copper 1 complexes generally aren't. Why is this? Now, if we look first at what we said gave transition metals their colour, it's in general, with the exception of the permanganate anion, a transition from a d electron, from dd. So if we've got an octahedral complex, say, an electron jumping from here to here is a transition that happens because some certain photon of light with the energy in the visible light region has been absorbed. So that's why things are coloured. So it's a D to D transition. Now, if we look at the electronic configurations of copper 1 and copper 2, it will probably become quite clear quite quickly. So copper as a metal has the electronic configuration of 3d10, 4s1. Now remember, this is the one that's the exception to the Aufbau principle. Copper 1 has an electronic configuration of 3d10, let's put the 4s1s in there, 4s0, and copper 2 has an electronic configuration of 3d9, 4s0. So if we look at 1 and 2 and draw their orbital diagrams, so this is for copper 1 and copper 2. We'll start with copper 2. We need to put 9 electrons in there. 1, 2, 3, 4, 5, 6, 7, 8, 9. You can see there's space for one more electron here. So we can take some light, shine it on it with a certain wavelength. The wavelength is also, the energy of the light can also be said, H nu as I did up there, sorry. And it will make a transition. An electron can go up, be promoted into this empty slot. Now, if we do the same for copper 1, we see it's got 10 d electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's no space for any more electrons to go anywhere, so we can shine all the light in the world we wanted it. But there is, no electron transition to be had, so none of the light will be absorbed. So then it's, for this reason that copper 1 complexes generally aren't coloured, whereas copper 2 complexes can be coloured because they can absorb light for this D to D electron transition.